Okay, now we go to the next subtopic, which is differentiation of hyperbolic function. So as you can see here, okay, there is equation 2.1, okay, and 2.2. So here it is defined that cos x or hyperbolic cos x is equals to half times ex plus negative x. So e here is actually exponent, so exponent x plus exponent negative x, and then we have a second equation which is hyperbolic sine x, which is equals to half times exponent x minus exponent negative x. Alright, so based on these two formula, right, so when we do the derivation or differentiation for the hyperbolic cos x, okay, so we are differentiating the equation here, and we will get this as the result of it. So half is a constant, so you can take it out, okay, from the differentiation. So we only integrate the exponent x and exponent negative x. So when we differentiate exponent x, we will get exponent x, okay, and when you differentiate the exponent negative x, so we just apply the power rule, okay. So you will get negative negative exponent negative x, right? This is a little bit special for the exponent function, yeah. So when you differentiate the ex, your final answer will be ex as well. And if you differentiate the power of negative here, you will get negative negative x, okay. So it turns out that the final outcome here is the same as hyperbolic sine, yeah, this one. So we can say that when you differentiate cos x, you'll get hyperbolic sine x. And similarly, when you do differentiation on hyperbolic sine, so we differentiate the equation, the second equation here, right? So what we will get is the final answer will be hyperbolic cos. So basically, the way we differentiate hyperbolic function is very similar to the trigonometry functions, okay. It's just that if you can recall, for the trigonometry function, if you differentiate sine x, you'll get cos x. If you differentiate cos x, you'll get negative sine x. But for hyperbolic function, if you differentiate hyperbolic sine, you will get hyperbolic cos, okay. But if you differentiate hyperbolic cos, you will get hyperbolic sine, okay, without negative. So, and the rest is so you don't have to memorize this, yeah. Actually, you don't have to memorize it, because during test or final exam, we're going to give you this appendix. It's a formula appendix. So this is the trigonometric substitution, the identities for trigonometry and hyperbolic, okay. And yeah, this is the, although this formula give you the indefinite integrals, right, but you can read it like this, yeah. So if you want to differentiate, wait, hold on. So if you are interested to differentiate this, so the way you read it, okay, this one is integrate cos x, you'll get sine x plus c. So this is integration process, because integration is the reverse process of the differentiation. So similarly, if you want to differentiate sine x, you'll get cos x. Alright, if you differentiate negative cos x, you'll get sine x. Okay, or other way. So if you want to differentiate cos x, so you will get here, okay, you will get negative sine x. So but because of this is integration, so you put dx over here and plus c. Alright, so you can see there is a list of integration, indefinite integrals, ranging from this is power rule. Okay, if you differentiate right now, if you it's not power rule. What I want to say is rules that involve with power. Okay, so we have xn. Alright, and okay, not this one, it's only up to this, sorry guys. Okay, and then here we have logarithmic, okay, or ln, and then we have from here to here, okay, we have this is trigonometry, and then if you can see, we have here is the exponent function. Then we have okay, let me scroll it. Okay, up to this is the hyperbolic functions. Yeah, and for the inverse function, this is later on. We will see this in chapter 4. Right, chapter 4. So don't worry, you don't have to memorize all these, but we will give you we will assist you in terms of giving you the formula. Okay, so we go back to this one. Yeah, differentiation of hyperbolic functions. Okay, and let's see some examples. Okay, so like I said just now, the way you differentiate this kind of functions, okay, for hyperbolic functions, is very similar. It actually exactly like the way you differentiate trigonometry functions. Okay, and you also need to apply the techniques, product rule, quotient rule, chain rule, whenever it applies. Okay, so here we start with one Roman here, y equals to hyperbolic sine 2x minus 5, and we have the second example here, which is y equals to hyperbolic sine power of 3 2x minus 5. Okay, one without power and another one with power. Okay, so now let's see the solution. Okay, again, here you need to apply chain rule. Okay, to answer the first question, just apply chain rule. You need to identify which one is u and which one is y, and you differentiate it accordingly before you can apply it on chain rule. This is very simple. Now we go to example 2 Roman here. So if we have just now sine hyperbolic power of 3 for 2x minus 5, again you can apply the chain rule. Yeah, chain rule. So we have first of all we have u equals to 2x minus 5, then we have v, which is sine hyperbolic u, and lastly we have y equals to okay, again, and y is v. Now we define as hyperbolic sine u, but here in the original question we have power of 3, so it will become v power of 3. So you need to find the u prime, the v prime, and y prime, and substitute the answer into using the chain rule method. Okay, so this is the final solution. Now we have exercise 2.4. Why not to try to do this? Okay, you can pause the video for a while and try to do this exercise, and this is the answer. Let me know if the answer is not correct. Yeah, okay, you can WhatsApp me personally. And now let's go to differentiation of logarithmic function. Okay, this is quite simple. Just now I already show you that integration of 1 over x. Okay, if you can recall that, integration of 1 over x is equals to ln x. So when you differentiate ln x, you will get 1 over x. And then if there is a function of f, ln f, then we differentiate it. Okay, we differentiate it. So this is the formula for it. Okay, you may look quite confused, but it's okay. Why not we try to link this formula with this example? Okay, we have here y equals to ln 3x minus 1. So you need to differentiate it with respect to x. If the u, okay, is 3x minus 1, okay, so again this is where we have to apply chain rule. So we have y ln 3x minus 1. So u is 3x minus 1, whereas y is ln u. So when you differentiate it, y prime, okay, you'll get this answer, okay, which is 1 over u. You differentiate u, you'll get 3. So by substituting it into the chain rule formula, alright, you will get 3 over 3x minus 1. So again, if we can relate it with this formula just now, when the function is function f, okay, you can see that there is a pattern there. If we can write it again, okay, we have y equals to ln f, where f is actually 3x minus 1, right? So f prime is 3. So if we just plug in using this formula, okay, you will get 1 over f. The f over the x is actually f prime, so I just put it as f prime. Okay, right, so your final answer will be f prime is 3 over f is 3x minus 1. So, well, similar to this. Okay, this is the shortcut one. But again, if the question asks you to use chain rule, showing it by using chain rule, you have to show this formula. Okay, you need to do step by step here. Okay, this one, and this one. Okay, I hope that one is clear. Now we have this one is exercise 2.5. So exercise 2.5, the answer is very So just now I show you exercise 2.5. So exercise 2.5, here I'm showing to you the answer for the exercise on chapter 2. So you can refer to this 2.1, exercise 2.1, 2.2, 2.3, 2.4, 2.5, yeah, 2.5. Okay, so we only got until 2.7. So you can screenshot and save this answer for your future reference. Okay, alright, so that's it. Until we meet again next week, don't forget to do all the exercises and the tutorial as well.